All right, so we're live on YouTube and looks like we're at the hour too. So once this loads, I'll get it rocking. Good on your end?
Yeah.
All right, here we go. Hello, everybody, and welcome, or for many of you, welcome back to KETIV Virtual Academy. My name is Tyler Hart. I'm with the marketing team involved in running these weekly training and thought leadership sessions. And today's topic is electrical design breakthrough with Ansys. Your expert for today is Graham Stevens, application engineer here at KETIV. Graham's a fantastic resource to the team, so happy to have him. If you have questions during the session, please submit them to the Q&A button at the bottom of your screen. We'll try to address them either during the session or at the end. And also, all these are recorded and available to distribute to your teams on ketiv.com or our YouTube channel. So definitely go check the historical sessions out. For the next events, I want to mention a few that are coming up. The upcoming KVA topics include Autodesk Plant 3D and Autodesk Vault. And we also have a special session on March 20th. This is part of our Manufacturing Leaders Exchange. You'll hear from Jim Huskinson, who is the VP of Engineering at Idaho Steel. It's a little bit more of a thought leadership than a technical session, but definitely worth attending. If you're interested in that sort of content, we also have more coming up in that general realm. So go check out our website and find those as well. So without further ado, I will pass things off to Graham to kick us off. Thanks so much for being here, Graham.
No problem. Thanks, Tyler. I'm an application engineer here at KETIV. I've been focused on Ansys products for quite a while, 25 years of product development, and I do high frequency and low frequency electronic applications as well as optics. And today we're talking about electrical design and how to improve our electrical designs, and in particular, the different workflows and different tools. I just want to make sure you're aware of all of the different options you have within the Ansys universe to simulate and improve your designs. And we'll also take a look at sort of some of the driving factors on where improvement comes from and then how Ansys can specifically help to do that. So typically when we're designing some sort of electromechanical device, and in this case, we're talking about transforming electricity into power. So we're usually moving something or sensing something or some kind of a motor, a power source, power transmission. And in those cases, we're typically looking at these kind of goals relative to the engineering efforts and product design. So first of all is performance. And typically we're always looking for higher torque, higher efficiency, higher power density, and lower weight. Especially in the aircraft industry, we're always focused on reducing weight. And then, our standard goals relative to safety and reliability, relative to compliance, relative to EMI, and then of course cost, reducing our prototyping costs, our engineering time costs, and then of course production costs as well. And so for today's seminar, I'm really going to focus on this electrical performance arena. How do we improve efficiency and torque and power density and lower weight? And we'll go into how to optimize what Ansys has in terms of optimization and improvements there as well. So as part of designing these sorts of electrical machines, typically you have multiple teams that might get involved. So we have somebody who works on the electromagnetics and somebody who works on the thermal side in terms of heat generation, which of course impacts the electromagnetics and vice versa. Or the mechanical side, you might have vibrations or structural issues. And then we might, on the electrical team side, is looking at the actual circuit design for the circuits and maybe the system level. And so all these different teams have to both talk together, and we also need to be able to model all of these physics both separately, but then also together in terms of how do they interact And so this is where Ansys's simulation tools really shine relative to having the capability of doing these sorts of multiphysics simulations to allow you to do trade-offs between physics and requirements, as well as share designs between these different teams and have these teams talk to each other effectively, even before you've built the product. And so when we think about electrification in particular, we have, again, multi-physics and multi-criteria. So we have electromagnetic issues or desires relative to torque and efficiency. We have the electrical circuit design relative to voltages and currents. We have thermal designs in terms of cooling, mechanical, and vibration, noise and vibration. And typically we're looking for high efficiency, high torque and power density, reducing cost, and then reducing the design cycles. And as you can see, we also have, 6,000 to 7,000 parts in a combustion engine, or, 30,000 parts, 50,000 parts in a jet engine. Obviously, if you're just designing a single motor or a transducer or something, you have fewer parts, but you still have some of the same issues. So Ansys can handle all of these, and we'll talk about how to do that as we go forward. And so when we think about electrical performance, getting higher efficiency, getting higher torque, typically in the engineering world, we're looking at both measuring these quantities, what is my torque, what is my efficiency, and then doing less with more, or doing more with less. And so the way to do that, of course, is to reduce your losses. And so today's seminar will be focused on all the different types of losses there are, and typical ways, kind of a checklist of different methods of reducing those losses that came from just sort of a broad brush survey of the electrical design universe. And then we'll be mapping those losses to different tools and different workflows that directly address measuring those losses, simulating those losses, testing different ways, whether it's materials or different designs or different ways to reduce those losses, so that we can make technical progress and do more with less. And so this is a list of your typical electrical machine losses. I am running a kind of a running list here. So if you see any losses that I've missed, please do email me so I can add those in. But typically we're looking at these types of losses. So on the electrical side, we have ohmic losses, your standard resistance losses. In a transformer core, we might have eddy current core losses and stray losses. We can have skin effects if we have current bunching, either in a high frequency situation. We have electrical noise, which occurs in the circuitry, dielectric losses, potential for demagnetization if you've got magnets and motors, radiation losses, switching, corona, mechanical windage and friction, operational, maintenance, aging, and thermal. And of course, for other devices, you might have optical losses or other things, but today we're focused really on just sort of electrical machines, the electrical universe, as our focus here. So this is just a checklist of different ways that people have used, engineers have used to reduce these losses. So ohmic losses, I might have an AC transmission line where I transform my DC to AC, transform to high voltage DC, and then that allows you to reduce the current for transmission, and then you transform back. In a transmission line, we might use a permanent magnet instead of a wire wound electromagnetic field inside a motor to eliminate the wire wound electromagnetic field resistance loss in a motor, etc. So we have all these different ways of reducing resistance, whether it's increasing cross-sectional area, reducing the length, the total conductor length, where if we're trying to move current from one spot to another, you just bring the source to where you're trying to get it to, and or reduce temperature. Similarly, on the core side, we might use low hysteresis materials, electrical steel or amorphous steel. For eddy currents, we might use, it's very common to use laminations or high resistivity materials. On the demagnetization side, we might reduce ambient temperatures or improve cooling, or simulate to avoid conflicting magnetic fields, which can demagnetize. And then, of course, for stray losses, you might want to simulate to improve your alignment, design, and construction of your device as a whole. And on the AC side, we have all these different types of losses, skin effect versus proximity effects. You might use Litz wire high frequency to reduce some of those. For electrical noise, filter harmonics, improve the power factor by matching, optimize the layout to reduce parasitic effects. For dielectric and leakage current, we look at using lower loss tangent materials. Radiation, you might want to improve shielding, and then switching losses, you might want to change the type of semiconductor that's doing the switching, or use some voltage. There's different power, PWM or switched mode, or different types of regulation methods to improve switching losses. So all of these are examples of ways that engineers reduce AC losses. And I just kind of provide this checklist as a way to sort of compare against your designs and see if there's some other possibilities in terms of your particular design goals. If we take a broader view and kind of move up to a more bird's eye view for a device, we might start thinking about operation and maintenance losses, as well as smart losses, or not smart losses, but just smart strategies to improve your operation and maintenance losses. And so with operation losses, you might, on the battery side, only charge between 20% and 18% to extend your battery life. You might regulate battery temperature. On the maintenance side, of course, you follow standard maintenance practices in terms of repairing defects and faults promptly. But we can also look at EMI and circuit protection to guard against power EMI issues, reduce contamination, corrosion, vibration, improve our quality. And then on the smart side, of course, we want to match load to supply more effectively. Use power management strategies or duty cycle management strategies, add sensors to detect failure early, a bunch of different ways to use sensors and get smarter about some of these losses that you might occur over a lifetime. And then finally, especially in the electrical realm, we find that thermal losses are important. And this is sort of the miscellaneous list. We have corona discharge, which doesn't occur that often, except where you have high voltages. But in motors, we certainly see windage and friction losses. And then on the thermal side, there's all sorts of different methods to improve thermal losses, whether it's improving heat transfer, where we're just moving heat from place to place, which is how a heat pump is more efficient than air conditioning. If we're changing cooling mode, using liquid versus air cooling, or just distributing the heat flow better in a design through conduction. Lots of different ways to improve our losses. And so this is one other example here, just looking at how cooling affects power and torque density for, happens to be electric motors, for EV drive motors or aviation motors or wind generators, and sort of how NASA is targeting higher specific power density over time, and a large chunk of that is through better cooling. So two-phase cooling, microchannel cooling approaches, going from natural convection to forced air to indirect liquid cooling to direct liquid cooling is a key way to improve your power and torque density for your designs. And so out of that loss list, of course, a large chunk of them, of methods to improve losses, concern materials. If I have a material that I'm looking for lower electrical resistance so that it has less ohmic losses, you might want to search for materials that improve your design. Ansys has a Granta materials database of 7,200 plus material records for high frequency, low frequency, all these different properties that are already categorized and found, so you can search through them and find and optimize your designs versus material properties, and really help identify some of these materials that could really help your designs, compare costs, etc. For the rest of today, I'll be just going through different workflows for these different types of devices. If we're creating electric motion using a vehicle, I'll start at the system level at some sort of vehicle, then go down to more of a motors, generators, and transducers level. If I'm transforming power from one type to another, AC to DC, or just moving it through an electrical circuit, we'll look at sensors, transformers, and power electronics, and what tools and workflows you might use there. And then we'll take a brief look at electricity storage and sources in terms of batteries and renewables. So if we think about the history of electric aircraft, this is just a slide here looking at from 1903, where we get powered flight, all the way up to first all-electric passenger plane in 2022. We're seeing more electric aircraft, and we're trying to decarbonize the system so it uses less fossil fuels. And this is at the bottom, of course, a bunch of Ansys tools that Ansys has sort of added to keep improving and keep moving in terms of getting your electrification and improving your electrification. The latest in this suite, of course, is MotorCAD, which has which we'll get to in a few minutes, in terms of analyzing motors and at a conceptual stage very quickly, to allow you to do these sorts of trade-offs in your initial designs. So if we think about just electric vehicles, whether they're ground or air vehicles, Ansys has a number of workflows at a bunch of different stages. So at the design stage, we can use MotorCAD to rapidly analyze different motor designs. Once you've search through the design space for the right kind of motor, we can then take that to a more detailed, feed that to a program called Maxwell to do advanced magnetics modeling, and really take a much closer look at some of those losses. We could then couple it and do what's known as multi-physics analyses, where we look at the structural implications, cooling, look at thermal in particular, and feed that back to the magnetics and make sure those all working together. And then finally, we can take that entire, now more detailed design and bring it to the system level through a number of different concepts. So we can pass that to the system designer of the car or the airplane and validate the system at that level. So the system level overview here just shows kind of the different types of components in this electric powertrain for this car, where we go from the power source, the batteries, to the inverter, to the power cables, to the motors, and then the system level design in terms of how is it doing mechanically in terms of dynamics and loads, and then controls. And Ansys has solvers for all these different levels. In particular, there's a system level solver here called Ansys Simplorer, which uses predefined models. There are multi-domain model libraries, which it then can do co-simulation with all these different physics, whether it's mechanical or fluids or electromagnetics. We have something called reduced order model creation. So if you're looking to have a reduced order model, is when I take a very complex, say, thermal situation, and I create a thermal model, and I extract the governing variables for that model, and then create basically an analytical equation that can solve that. CFD simulation very quickly, and then I can pass that analytical equation up to the system level where I can do system modeling more effectively instead of having to wait hours for an FEA analysis to be complete. And then finally, of course, we have embedded software integration as well. So if you're looking to do embedded software for your vehicle, that's possible with Ansys Skate. And as I said, we have different levels of modeling for electric machines. Ansys has a simpler equation-based model, so very simple, more at the circuit level, formulated from first principles, but it neglects the detailed losses. And then if we move to finite element analysis in Ansys Maxwell, we can do reduced order models, as I said, where we do a complicated FEA model, extract the governing variables, and create that reduced order model so it runs much faster. And then we can also go to the transient level and consider eddy current losses, core losses more accurately, but obviously it's more computationally intensive. So we go from kind of seconds here on the equation model basis to maybe minutes on reduced order model to hours and a transient, depending on your level of accuracy desired and what you're looking for here. And this is just a very rough sketch of different types of reduced order models in Simplorer. We have linear reduced order models, nonlinear static, and nonlinear dynamic. And if you're interested in exploring how to do reduced order model creation, please do give us a holler here at KETIV. And then we'll jump from the system level now down to, well, let's look at a motor. How do we design just a motor? And for this, we have a tool called MotorCAD within Ansys. It's a class-leading tool for electric motor design. It has a number of standard templates, whether it's an induction motor or a permanent magnet motor. There's templates in the design where you just kind of pre-built everything's there for you, and you just have to start changing how big is it, what are some of the parameters I want from it, start getting predictions almost immediately. It's equation-based models that are combined with 2D FEA to get very relatively rapid, within minutes, 5-minute simulations of your electromagnetics in your motor, the thermal design in your motor, mechanical NVH, and then lab-based in terms of duty cycles. And so we sort of start with, we have a motor, we define the type, input all of the different material and design specs in terms of what it looks like, and then we can get efficiency maps and NVH predictions, motor stress, rotor stress, etc., and at the design stage. And then once that's complete, we can take that initial design where you might have, you took the universe of thousands of potential designs down to a half a dozen or less. And now for each of those individual designs, we can evaluate our losses much more with much more fidelity and accuracy, and really take a deeper look at, okay, if I change this little radius right here, does that impact my losses or not? If I tweak this or tweak that, and get a real optimization for all these losses. And so Ansys Maxwell is a general purpose tool in terms of looking at your electromagnetic fields and calculating all of these different kinds of losses to a much higher accuracy, and then integrate them with other packages. So we have motion here. You can sort of see the motor and how it's doing on the transient side, etc. And then these are just some other potential losses that you might be interested in. If we're looking at torque ripple, if we're looking at unwinding effects, eddy current losses, magnetic segmentation, demagnetization, the impact of PWM voltage pattern and motor losses, all of these different things can be evaluated within Maxwell. And I mentioned the thermal analysis briefly relative to MotorCAD. MotorCAD has a lumped parameter thermal network. And so you can sort of see this spaghetti diagram, at the bottom here. And so this is a thermal resistance network of the different parts of a motor that's been done over time for all these different motor types. To get sort of typical, measured and validated motor designs. And then it uses that to estimate thermal performance very quickly. But we can also take the MotorCAD design and throw it into fluent or ice pack or mechanical, for that matter, on the conduction side, and get a much more accurate picture of what's going on in terms of cooling. And so we have this capability of doing, fast and quick, but maybe slightly less accurate, and then going to a more detailed design and much more accurate on the CFD side, as an approach to getting, quick and dirty answers right at the beginning, and then getting to our detailed design as we go forward. And then on the transducer side, our workflows are pretty similar. A couple of different tools that are added in. Something called RM Expert or PE Expert allows you to analyze electrical machines and power electronics. So RM Expert has a number of other templates for electric machines similar to MotorCAD. PE Expert focuses more on transformers and inductors. And again, sort of creates automatic designs and gets you through the design space. And then you can evaluate those preliminarily and then feed them into a Maxwell analysis. And then Maxwell might talk to Simplorer or Twin Builder at the system level to look at how am I driving this motor or this device. We might use Q3D or SI-Wave or HFSS to look at RLCG parasitics or S parameters, and Ansys Mechanical for thermal and stress, or Ansys CFD, again, for thermal if we have convection involved. So all these different tools sort of talk to each other seamlessly and work together to get your final picture of different types of losses. And our transducer here is a little, the workflow here is very similar here, where we have Q3D, mechanical, Maxwell 2D or 3D, P Expert, RM Expert in the design, and we can use optometrics to optimize the design. So optometrics is when I might take the size of one of these teeth, or it's, the number of the teeth, and I create a design that varies that parameter. And then I might do a parameterization study where I vary that parameter and see, well, how does my efficiency improve or not improve if I change that? And so we can do parameterization studies and relatively simple, like 1 to 10 variable optimizations as well, directly within Maxwell for transducers. At the sensor level, we again might use Maxwell to look at more detail at the magnetics and what's going on there, and then create a design of experiments or as a reduced order model for the sensor that we can then pass up to the system model for use in the system model, where we have, if the teeth here gets close to the sensor, we have a certain voltage that comes out of the sensor, et cetera, and pass that to system simulation. So now switching gears slightly to power transformers and planar electronic transformers, we have roughly the same tool set. A couple of different tools here: Maxwell UDPs, CAD import and Excel scripting for model creation for power transformers. Again, feeding into Maxwell, using Simplorer and Q3D for parasitics and optometrics for parameterization and optimization. For electronic transformers, there's in electronic transformers ACT module that again has electronic transformers templates sort of designed in it, and something called PE-MAG that allows you to explore electronic transformers as well. But again, roughly the same flow. We're feeding it into Maxwell and passing models back and forth between a thermal modeler, whether that's mechanical or ice pack or otherwise, and then passing, going up to Simplorer for the system level analysis. And then if we think about other aspects of power electronics, I think we covered most of these in terms of multi-level modeling, different levels of thermal analysis. EMI, EMC, I'm going to be covering in next month's webinar or 2 months webinar from now. So we'll skip that for now. And embedded softwares and controls is the SCADE product. And I just wanted to make you aware of both reduced order models in slightly more detail, as well as PCB reliability capabilities. So for power electronic systems, we can take a bus bar and then look at use Q3D extractor to get LCR parameters, create a state space model, and then plug that into Simplorer. So for a lot of these different types of electronic components, whether it's sensors, bus bars, battery packs, cables, machines, and actuators, think about using a reduced order model when you're then moving up to the system level and modeling it there as well. And then on the reliability side, and this is more on the maintenance losses, where you might have a PCB aging or not performing as expected over time, we can preliminarily evaluate a PCB's reliability by using something called Ansys Sherlock. And it has basically a whole bunch of a database for a reliability focused database for PCB components. We take our PCB components, feed that bill of material into Sherlock. We can get a preliminary analysis immediately, almost immediately, a few minutes. And then we can refine that analysis by doing additional FEA analyses. So we might look at signal and power integrity in SI Wave or HFSS 3D layout. We might look at temperature within ice pack, shock and vibration analysis of mechanical. All of those additional analyses improve the accuracy for Sherlock. And at the end, we can get a mean time between failure for our PCB, PC board and or potentially systems. And if we think about batteries, Ansys has a lot of battery capability. We've been doing a lot of work for lithium ion and a bunch of other different battery technologies, flow batteries, etc., down to the very detailed level. Most of this work is actually contained within Fluent. And so you see at the upper left here a CFD, so looking at the cooling of batteries and battery packs. We then have ECM models on the electrical side, the circuit side, where we look at that. And then within Fluent, there's also an electrochemistry model, especially for lithium ion, where we're actually modeling electrochemistry and seeing how that's impacting the thermal aspects of the battery and what's going on, and especially, of course, focused on lithium ion, where it has thermal runaways as a potential issue, and needing to model that carefully to make sure our battery doesn't catch on fire or explode. So all of this is within Fluent, and we have capabilities there. And so on the workflow side, there's as I mentioned, there's a lithium ion battery model inside of Fluent. We can look at cell and battery pack thermal flows within Fluent, and then bring that up to an equivalent circuit model in Ansys Twin Builder, Simplorer, to get a better feel on what's happening at the system level and integrate. And so when we think about optimization now of I have different losses I'm playing with, or they're playing with different materials or different design options that I want to explore to see if I can reduce my losses. We have a number of different steps on the optimization side that you can take. The very first one that we advocate is doing a sensitivity analysis, getting a broad brush of everything you could vary, and then identify out of all these, maybe 50 parameters, 100 parameters, which of them is really important. and how much do they impact my final efficiency or my final resistance loss, and understand those input-output dependencies and interactions. So you might do a sensitivity analysis. We can do that kind of variable by variable by doing a parameterization in optometrics inside Maxwell or HFSS. There's also an optimization tool there as well within optometrics. And then as we're getting into more variables and or wanting to do Monte Carlo analysis in terms of tolerance variation for manufacturability, you might want to think about another package called OptiSlang, which is basically optimization on steroids. And it in particular has a method of the optimization algorithms are very efficient so that we don't have to when I'm exploring a design space of thousands of different potential designs, we only have to maybe run 50 simulations or 100 simulations to fully explore that design space. So it can save you a huge amount of time and effort, especially when we're talking about multi-objective optimizations and or multi-physics optimizations. So things get complicated fast, and having to, make sense of it all, OptiSlang can really help. So as I mentioned, you've got this balance between accuracy and computation time at different levels. So we might use MotorCAD at the beginning of the design, but then want to get a more detailed design. And with the more detailed designs, of course, if you're doing an FEA analysis and it takes hours to run, you want to reduce the total number of runs as much as possible. And that's where OptiSlang's meta model generation methodology can really help reduce the total number of designs that you're doing. So in this particular case, we were using MotorCAD to do all these designs. MotorCAD solves in minutes, so we can solve a lot more designs more quickly, and so that's where all this dot plot gets shown. But we can do the same thing in Maxwell as well. And so workflow-wise for OptiSlang, you usually use a script to define a sensitivity analysis, and then create a meta model. It's called a meta model of optimal prognosis. So essentially, we're modeling, we're creating a prediction of how these variables interact with each other, and testing that prediction is what this meta model is about. And then from the learnings from that, we can then start optimizing and create an optimization function. Say, I want maximum torque and lowest weight, or I want lowest cost, which might be, say, total volume of a magnet or something. And we have these two different parameters. We're playing off each other. We might weight them and then optimize our design towards that optimization function to solve for what out of my 50 parameters, and what size and variations are going to satisfy that optimization algorithm in terms of what we're searching for. We use all of that to define and find a couple of designs, and then of course we go back to more detailed design within MotorCAD, within Maxwell, to validate and make sure, yeah, we got it. So an example of this is just an induction motor here within MotorCAD. You can sort of see, rough temperature limits, size, etc. There's requirements and goals here in terms of specification, in terms of operating speed. We're looking for max torque and peak power. We want to have a good motor here, demagnetization, all these different types of goals, and we have to satisfy them all. It might look at torque ripple, rotor mechanical stress, peak continuous performance, manufacturing constraints, all of these different goals or different requirements. And at the same time as all these requirements need to be met, we're wanting to minimize our magnet mass and minimize our losses. And compare this to different types of vehicle motors out there. This is an electric EV database, just sort of showing rough performance of a vehicle at the top level, which we're trying to design for. And so we start with a baseline design from MotorCAD. You can start relatively quickly with only changing a few parameters of the ratio-based design, get to an initial design. and then start looking at its cooling system and define that. And sorry, I hope this doesn't get, we can see this. So this is kind of where the baseline design was. So we start somewhere and we look at, oh, our baseline, maximum torque, peak torque is not really met. Our continuous torque is not really met. How do we get there? And we want to, find the best compromise between magnet mass and drive cycle losses and fulfill all these requirements at the same time. And so to do that, we would do a parameterization of all these different potential parameters we can vary or change, whether they're ratio based or fixed, or we change material from X to Y to Z. We look at the different, and this parameterization, we then define, okay, the bridge thickness can go from 0.5 to 1.8. The magnet post can go from 0.5 to 3.5. So we define reasonable ranges that we might design this motor towards. And this is a fairly large design space. If you were to do iterations on all of these, it would take you years to actually look at them all. And so this is where we parameterize the design, so it will vary, plug in a new arc ratio and we immediately get a new design, which is how MotorCAD works here. And then start exploring that using the meta model optimization process within OptiSlang. So as I mentioned, rather than doing a direct optimization where we have thousands of designs to just kind of brute force our way through, we create, we start testing designs and then start creating a meta model of, well, the surface of this, the design surface for this design looks approximately like this. And that allows us to make predictions of, well, if I choose a new input space here, where is that actually going to lie? And then we test our design against that prediction, essentially, make sure we've got enough samples to validate and verify the prediction. And then once we have that meta model, we can then start using the optimization function to immediately say, aha, I want to get to higher torque. I need to be in this range of variables, and that'll explore design options, just explore different points in your design space to get to that optimization. And as I mentioned before, this is all integrated with MotorCAD through Python scripting. It's automatically generated from a dedicated MotorCAD both user interface and you have a script here. And then we can start looking at torques, or looking at results. So this is an example of our prediction of peak torque and which variables are most important for predicting peak torque. So it looks like the stator bore ratio and the L1 pole V angle enable you to predict pretty well what the torque is going to be. We have torque ripple, where this time rotor skew angle is important, and the magnet thickness. And then losses across the cycle are improved by the pole V angle L1 and split ratio, etc. So we start getting a good hard look at what's impacting our design, what makes the most difference, and then we can use that to find the total combination that gets us, meets our performance targets, gets to cost versus efficiency ratio, it's suitable for mass production, and meet all of our goals. So just want you to be aware of that tool. And then I'll probably finish here with, this is just a loss to Ansys tools mapping, at least in the electromagnetic space. Where I had my list of losses, and you can refer back to these slides or refer back to earlier in the video, which will be live on YouTube for later. And if you're looking to reduce core losses, which Ansys products, which workflows do I want to start looking at? And this will give you a preliminary indication of where to go. And then which workflows, which tools might make sense. You can sort of see that Granta materials, there's almost always a material thing you can change to improve your losses. And there's almost always a way to optimize. So that's why OptiSlang and Granta here are all. Wanted to then pause now for questions. Wondering if anybody has any questions.
Thank you so much, Graham. We'll wait a couple seconds here for questions if anybody has any. Just a reminder to everyone that Graham has all sorts of great content out on our YouTube channel and also on KETIV.com/KETIV Virtual Academy. All of this is recorded. People are sending it all around to each other and learning a lot. So use this as a resource. We're always here. We have a lot of great minds like Graham's on the team, and that's a great resource to learn more.
Yep.
So I'm not seeing any huge questions coming through, Graham. So
okay.
Wrap up when you're ready.
Sure. So just to conclude, Ansys can solve your electrification design challenges and improve your performance, especially by focusing on electrical losses. And then just a few slides here of additional resources. So in particular, please do email us here at support@ketiv.com if you have any issues. You need further guidance as to how do I do this, how do I do that. Ansys has a learning hub, which is a repository of webinars and courses. So there's an electronics learning room, a MotorCAD getting started, a Maxwell getting started, if you're looking to just get started and diving into working on these types of simulation problems. And then we have additional support as well. So Ansys has a how-to YouTube channel. You can find a lot of good videos there, webinars at this resource, and something called the Ansys Innovation Space, again, for mini courses to help in this arena. So just want you to be aware of all those different resources and take advantage of it. And then also, if you are constrained relative to your own engineering resources, please be aware that KETIV itself does simulation services for customers. So we can do all these types of analysis for you at 100%. We also tend to do a lot of training. And so we have the customer doing this at 100% and sort of anything in between. And so we're happy to fill in. If you don't have an electronics reliability resource, we can do that for you initially and then get you up to speed depending on what makes sense or not. Same thing on the mechanical side, same thing on the fluid side. So please do keep us in mind if you're interested in consulting. And with that, I am finished.